Let's talk about exactly that, iterating faster on stateful services in the cloud. Denise gave the great introduction for us already. Let's talk about what we're going to talk about. One of the first things that we're going to be discussing is what makes stateful services special. All of you probably have a kind of hunch or intuition for what makes your stateful workloads special, but we're going to be doing a deep dive into that and kind of analytically looking at it and seeing what makes them special and then what we can kind of do about that. But we'll also be talking about the why, because there's a reason you're all here. It's to iterate faster on stateful workloads, sure. But we need to talk about the why, because in the end, we're not really doing it for fun. We're doing it for good reason. And then the meat of this talk is going to be exploring your options. Netflix does it a particular way, but that's not really the most important part about this talk. The most important part about this talk is empowering you to analyze the options that are out there for deploying stateful workloads and picking the best one for your particular environment, for your particular risk and iteration speed requirements, and that sort of thing. So let's see how that works. No, that's OK. We can use the keyboard.
Yeah.
So let's talk history first. Yes?
Yes, a bit about history. We're going to talk a bit about the what is a stateful service, the why, and the how. But before that, let's dive into a bit of history. So in a not that long time ago, in a not that far valley, there was a small company called Netflix shipping DVDs through mail. They were doing some streaming, but not that much. And the year was 2008. At the time, we were serving our customers through a data center infrastructure, and we had a major meltdown. We couldn't ship DVDs for days. That's when we decided that something had to change. Our mission statement was to entertain the world, not to run data centers. So that's when we started thinking about moving to AWS, EC2 in particular. And so for the first 2 years, 2009 and 2010, we focused on stateless services. They were the easier to migrate. But then in 2010, we decided to start trying to migrate our data stores, our stateful services, to the cloud. And our first solution we took was AWS SimpleDB, which no longer exists now, but you can think of it as the predecessor to DynamoDB. And so for about a year, we started migrating some use cases to SimpleDB, but we decided we would be better served by running our own Cassandra servers, and that's when we pivoted and started running Apache Cassandra in AWS. You'll see two different forks in the timeline here. There's the mutable infrastructure fork on the top and the immutable infrastructure on the bottom. But first, what do I mean by immutable infrastructure? And so immutable infrastructure is a way to deliver software through AMI, Amazon Machine Image. So that means you don't modify instance in place, you don't update any software in place. When you want to deliver new software, you bake a new AMI, and then you do what we call a red-black deployment, which is you start new instances that will launch with the new AMI, and then your old instances are going to be drained out of traffic and then decommissioned. Red-black deployment. And that was perfect for stateless services. But for stateful services, it didn't give us the solution we needed because it came at a cost. Like the red-black deployment works fine when you don't have state. But if you have state to move to your new instance, then their deployment is going to be way slower and didn't achieve this deployment speed that we needed at the time. This is when we moved to a more mutating infrastructure. So anybody here ever tried to run apt dist update in production? That's not a good idea. But for a couple of years, that's what we were doing. We were updating in place instances through dep packages and yum because we were running both CentOS and Ubuntu. But then after a couple of years and a couple of outages, we figured out that it would be best to go back to the immutable infrastructure, but with a twist. In 2018, one of our colleagues, Joey Lynch, did a reInvent talk when he talked about iterating on stateful services in the cloud. So you can see a similarity in the title here. What we're giving is a 5-year update on what we were using at the time, but also what we're moving to, which is a way to iterate even faster to the cloud. And that way to iterate in the cloud without doing the red-black deployment, but still, still using an immutable infrastructure was what we called AMI flashing. So AMI flashing is a way to replace your root volume, but without touching your ephemeral store or external EBS data. And so in a way, you replace your instances with new software, but you use the same EC2 instance. You just replace your root volume of that. And that served us very well for a couple of years. And we've been using that strategy until recently, where we still use that strategy, but with a twist, and we'll talk about it a bit more later. But we found a way to iterate even faster with containers, which we will also cover.
Thanks, JS, for that history. Now, normally, I wouldn't say that the history of Netflix's stateful deployment services are like that important, because who really cares about what we were doing 10 years ago? You might say it's just kind of like a cool story, bro. It's just not that important for today. But I promise you it is. And it's not that Netflix's history is so important. It's about the context in which your particular environment grows up with stateful services, because they just don't live in a vacuum. They live in a tightly coupled world with your deployment system and your configuration management system, your service discovery system, all these integrated systems. And we did this change. You saw the schism between immutable and mutable, and we moved back again for good reason. It means that we were doing a kind of calculus. We were deciding to pick mutable deploys in order to get some iteration speed. And then later, after outages, we decided to go back because our risk tolerance became higher. So we decided to change our mind and go back to immutable deployments because we didn't like that risk. So we were willing to give up some speed. It's this exact calculus that I want to empower you all to be able to do in your own environments with your own options. And we'll talk about all those. But we're getting a little bit ahead of ourselves. We haven't actually talked about the stateful services themselves and what makes them so special. On the screen is a set of production stateful workloads that Netflix actually runs. And you might be surprised that up here is lacking the kind of Amazon managed services, but I promise we'll talk about those in a second. But these are real. These are things that Amazon has decided to run purposely in order to achieve some particular business goals, or perhaps to run some auxiliary software. And we do all of this in a stateful way, and we'll be demonstrating how we actually do that. But these are just examples of some of these services. Should be pretty familiar. But what makes them even more familiar is perhaps what makes them special. And of course, that thing that makes them special is they're full of state. They have state. If you launch any one of those databases from scratch with no state, it's just not very useful. Of course, you wouldn't call it a deploy. You'd call it an outage because there'd be no data for you to access. So without the companion data that goes with the thing, at that particular database, it's not useful. Again, this is a little obvious, but it helps to really remind yourself of that. It's the state that matters. Another thing that makes stateful workloads particularly difficult to deploy is perhaps their associated sidecars or different components that go along with that stateful workload. And these are things that often go along with a distributed database, things that have to handle things like replication management or up-down, kind of like making the database available or not in a particular topology. This is often a separate piece of software that's interacting with the database. And so this is the kind of thing that can make stateful services deployments difficult. And of course, we have to hit upon the gravity, the actual size of the data. But let's actually look at that data size a little deeper in an analytical way. Take a look at this cool chart. We'll spend a bit of time in this chart because it takes a while to kind of grok. On the y-axis, we have time to fill. Time to fill is the size of this particular EC2 instance type, whether that's the memory or local disks, divided by the network bandwidth, the theoretical maximum pipe size network bandwidth of the thing. And so when you divide those two, you get the best case scenario of how much time it would take to fill up that EC2 instance with full of data. Again, theoretical. Obviously, it takes a longer time depending on the actual database type. On the x-axis is cost per gigabyte. This is just if you took, again, the memory or disk associated with the EC2 instance type and just divided by how much it costs, you'll see how much it costs per gigabyte. So if you have a database that can shard or grow linearly, it might make more sense to launch more smaller instances that are more cost-effective compared to one big one that might be just too expensive. So this is a cool way of evaluating the instance types available to you at Amazon. I did this analysis recently with many of the newer class of instance types. But the more important takeaway here is this trend line of of cost to time to fill, because there are instance types that take mere minutes to fill up all of their data because they just have a great ratio of size to network. On the other hand, there are instance types that take on the order of hours to up to a day to fill up all of their data. And so if you're using a deployment system that involves transferring state like we used to, or still do today in some circumstances, this is a very important consideration, especially if you're using a distributed system that has many database shards that each need to do their own fill-up. Because if you have a 100-node Cassandra ring, you may be paying that 1 day cost times 100. You know, if you're trying to spec out how long it's going to do to deploy, you're looking at a long time. So this is a great way of kind of visualizing not only the best EC2 instance type for your particular stateful workload, but also as a reminder that this is the kind of gravity that we're talking about when we're talking about stateful compute and what makes it special.
So Kyle just covered the what and a part of the why about stateful services, but another part of the why is it critical to iterate faster? And the first reason is security risk mitigation. I'm going to test memory of the crowd here. What happened in December 2021? Yes, Log4Shell. We all remember. By the way, I didn't draw that. That was my daughter, but I couldn't find a logo to put there. But she wanted to contribute to the slide, so that was her contribution. So security risk mitigation is the #1 reason you need the ability to iterate faster on stateful services. But there's other reasons. The second one would be there's a business risk of not iterating fast enough. If your iteration speed can impact your innovation speed, then you can definitely slow down your innovation, which is a problem. And for us, it would have been a problem because recently Netflix launched new ventures, Netflix Live, as well as Netflix Games. And these new offerings require different kind of data storage solution. And so we needed the ability to iterate fast on those because they were needed for a project that was on a very accelerated timeline. Another way to think about this is if it hurts, do it more. I'm going to draw a parallel here to chaos engineering. Maybe some of you knows the concept of the chaos monkeys, where we launch a system that terminates instances in our production environment so that we can make sure that all our systems are highly available and can sustain unexpected failures. Well, if you need the same thing for your stateful services as well so that you can iterate fast enough. And so having the ability to do it often, iterate faster on software changes, means that if something happens, you have to move fast, and you already exercise all of those muscles. And here are some hints that you would benefit from iterating faster. So these are phrases you might have heard or have said in the past. We can't reboot the MySQL master. Don't restart Memcache. Or we would take a downtime to upgrade Postgres. Or the website will go down if we lose the primary Redis instances. And that's all true if you don't have a highly available deployment system. So if you don't have a multi-MySQL master system or any of those. Of course, if some companies can handle like daily 1 hour downtime for migration, but a 24/7, 365 business can't. You need to make sure that you can iterate fast without impacting your availability.
Totally. And I've been in this industry long enough that I've heard all of these excuses, and some of them multiple times in the same company. Different companies have different needs. And I've heard all of these, and I thought to myself, this doesn't sound right. It doesn't sound like the kind of excuse we should be making as engineers. So we're here to tell you, if you're in the audience and you're listening to these and you're thinking to yourself, oh yeah, we're totally not in a situation where we just restart Memcache or something like this. I'm here to tell you that this is not an excuse to say that you can't iterate quickly in the cloud or on your stateful workloads. Because in fact, if you're saying any of these things, your iteration speed is effectively 0. It means you cannot iterate, you cannot restart, you cannot reboot. These aren't excuses not to iterate. These are kind of business reasons to make the case that you must invest in your stateful workload deployment mechanisms because of all those business reasons. So I just wanted to say, they're not excuses. They're wake-up calls, really, I think.
Yes. So now that we've covered the why, hopefully by now you're convinced you need to iterate faster on stateful services. Let's talk a bit about your options. I'm going to hint to the first option by saying a quote that Charles Phillips said in 2014, "France, don't let France build data center." And we fully agree with that. We on board on the moving our stuff on Amazon's web services, and we did. But that's the key lesson here is focus on your mission. Like if your mission is running computers, then do so. But if your mission is entertaining the world like us, then we don't want to focus on that. So we're taking that quote and we're doing a quick spin on it. Friends, don't let friends build stateful services. Which brings us to option 0.
Option 0, I mentioned that we would get to this in a bit. These are a list of some of the Amazon stateful services available. They're all managed services. And indeed, Netflix uses many of these. And then the reason we use them is exactly for what JS said. Our business isn't to run even computers, it's to entertain the world. Therefore, whenever possible, we use services that can do that for us and just eliminate a huge class of complexity and concern for us. Only in the cases where these are insufficient or perhaps cost too much will Netflix invest on a stateful deployment mechanism for some particular data store. But if at all possible, we do pick these. So assuming that these aren't available, and you do have to deploy something special like we have at Netflix, let's talk about some of those options. Because if you are going to deploy, one of the first things you're going to need to choose is which road you're going to pick. Remember in the beginning, we showed the timeline where Netflix split and started doing mutating infrastructure and merged back with mutable for their stateful workloads. As just a reminder again, the immutable branch means that you're deploying in an image-based approach where you flash the instance or you boot the instance with a particular OS once, and you don't change it over time. And if you do make changes, you give it a new OS. Versus the mutating branch, where you start up and then you mutate that on the fly, and then your OS kind of drifts from what it originally started with. Just keep that in mind, because all of these examples are going to be instances of one or the other or a combo. This first option I'd like to bring up to the forefront, configuration management. I put industry standard best practice with a question mark because in 2023, I'm not so sure if it's actually the best practice, but it's certainly a very common practice. Puppet, Chef, Ansible, Solve, I've worked with all these things in different situations. And I can tell you that, and you'll probably agree with me if you've used one of these tools, is that they can be brittle. And the reason they can be brittle is not because they're necessarily bad tools. I think they are actually all good at what they do. But the problem that they're trying to solve, that idea of mutating state on a server, is difficult and error-prone. When it comes down to it, these tools have to input a kind of huge combinatorial explosion of potential inputs from whatever the server's state is, and then try to converge it to the desired state that you've defined. And that just has a lot of things that can go wrong. This is why I don't particularly recommend this approach to stateful workload management because of that error proneness. And you saw that in our timeline for Netflix, we veered back into the mutable world, immutable world, away from this kind of thing because of the risks involved with doing this. Just as an example, if you're using Puppet to bootstrap your MySQL servers, if Puppet is down or the catalog isn't working for some reason or someone just made a typo in the Puppet code, you won't be able to bootstrap a node in a hurry. Whereas an image-based approach, you can kind of guarantee it's going to launch. Anyway, so configuration management, it's not bad, but I think we can do better. And we would like to present some more. A second option that I think is underrated in the industry is this replace root volume API. And to me, this is a cloud-native approach to actually iterating on stateful workloads in a very fast way. If you don't know, this is just a screenshot of the console, but you can take an EC2 instance, click on it, click on the thing, and then replace its root volume with a new AMI if you're choosing. This allows you to do an upgrade of your OS or change the software versions. Now, the thing is, it does take the server down, replaces the root volume and brings it back up, so you experience some downtime, but you'd have to experience downtime regardless if you're going to restart MySQL or whatever the case is. So you're going to need some orchestration, but it is really fast because it's happening on Amazon's kind of data plane behind the scenes. You don't have to transfer any data around. And if it's not obvious, when you bring up the server back up, the data on the auxiliary disks or attached EBS is left untouched. So it's just kind of like a long reboot, really. But when it comes back up, it'll have new operating system. So again, this replace root volume API, or using the console, I think is an underrated way of getting new state in an immutable way, because you're using the flash, you're flashing the OS, without too much rigmarole. And this is the thing that JS hinted at when we were doing on the other timeline. We were replacing the root volume underneath behind the scenes like this. So it's a good approach. We can't have this talk without talking about Kubernetes, because Kubernetes is so hot right now, and there's this strong desire to unify things, because it's on the surface it seems like a good API for deploying code, and it is. And in fact, and at Netflix we use plenty of Kubernetes, but for running stateful workloads, I can't exactly recommend it. And Amazon provides EKS, a managed Kubernetes environment, and you can install EBS plugins and use stateful primitives, and you can deploy stateful workloads on EKS or just Kubernetes generally. But it comes at a cost, and that cost is complexity. In order to deploy a stateful workload on Kubernetes on EC2, you have to understand the underlying primitives that Kubernetes is using to get that state in the right place and launch the right containers in the right way. You have to understand persistent volumes, persistent volume claims, headless services, all the things, kind of all the things revolving around Kubernetes. You must be an expert. Lee Briggs coined the 300% problem as the description of what this actually is. The 300% comes from just adding the 100% of knowledge that's required to really understand the actual application you're deploying in a distributed way, like MySQL. You have to understand MySQL, the MySQL replication, bin logs, all those things. That's 100%. Another 100% comes from the fact that in order to deploy this on Kubernetes and operate it successfully, you need to understand 100% of what Kubernetes is and how it works, how pods are scheduled, PVCs, PVs, all those things. That's another 100%. There's another 100%. That other 100% comes from the operator or stateful set controller that's interacting with Kubernetes and interacting with MySQL, the two, to orchestrate deployments and reboots and all the things. That's its own code base with its own idiosyncrasies and behaviors that you must be able to understand and troubleshoot. You need to get its logs and understand what it's doing. All these combined is the 300% problem. So if you're going to deploy a stateful workload on Kubernetes using these primitives, I don't recommend it because of the high complexity overhead, unless you're a shop that already has a lot of Kubernetes experts and a lot of Kubernetes operator experts, and happens to have a good overlap between that and the people who own the applications, MySQL, Postgres, whatever it is. Because if it goes down, you're going to need an expert to bring it back up. So Kubernetes, it's an option, but it comes at a cost. Let's talk about this next option, and this is going to be the option that we're going to demonstrate and talk about because this is how Netflix does it, or is beginning to do it on some subclass of some of our workloads. We're calling it standalone containers. It's kind of a hybrid between Kubernetes and just raw EC2. It works by using a normal EC2 instance and then running kubelet, which is one component of Kubernetes. It's just the component that runs on a Kubernetes agent that actually runs containers, but running it in a standalone mode. If you didn't know, you can run the kubelet in a mode where you just give it the raw pod.json, a static file that has the container definitions to bring up a particular set of pods together, or containers together. This is one way of getting the benefits of having container-based deployments. So you have fast, rapid container builds and deploys without the complexity of a Kubernetes cluster. There's no Kubernetes cluster in the mix here, standalone. There's no PVCs or PVs. There's no controller doing any shuffling. There's no scheduling, nothing like that. So standalone kubelet. It's an immutable approach because the containers are the new unit of deployment, and those are immutable, or we treat them as such. The data, though, is still on the EC2 instance on the auxiliary disks. They're just bind-mounted in. They're not really volumes exactly. They're just bind-mounted directories on the host. So again, it's kind of a compromise between a dedicated EC2 instance, still get containers, still using kubelet, but just in a very straightforward and a little easier to understand way. For Cassandra, this would be just an example use case of this. We would have a Cassandra stateful EC2 instance, standalone kubelet. In the Cassandra instance, we'd be running a container for Cassandra, sure. And then a sidecar container. At Netflix, we use a sidecar called Preem, which does the orchestration and backups and that kind of stuff between a Cassandra ring. And another example container would be OpenTelemetry, which is just a logs and metrics sidecar open source. But this is an example of just a classic pod with multiple containers running a workload together to achieve a particular goal, each of which can be upgraded independently. You can change which version of each of those things are on the fly. Not on the fly, but So for this particular example, like I said, this is the one we're going to demo. We'd like to dive a little deeper for you and explain how it works actually in action. For an actual stateful workload developer at Netflix who's looking to deploy a new version of Cassandra or deploy a new stateful workload, they're going to start at the left-hand side of this chain, which is the SBOM, the software bill of materials, industry standard term. But it just means it's a definition. It's YAML for us, but it's not the Kubernetes YAML you might be familiar with. It's the YAML that we've defined. It handles our business needs. It's a YAML for engineers to work with, to define the components and pieces of software they want running on this standalone EC2 instance in the containers. That gets compiled into a version set, which is a JSON file with locked versions of every piece of dependent software that's going to run on that EC2 instance. We do this because we don't want things drifting. We want things to be understandable and repeatable. So we want a completely reproducible build. And so the version set is the actual locked thing that we use to really talk about what version we're deploying, because it contains all the subsequent dependent versions. But a human doesn't generate it. It's locked during CI/CD time. Finally, the pod spec is compiled at the very last second on boot to give the kubelet a definition that it can understand and run. A human is not creating this pod spec. It's a function of the input version set. But it takes all of the containers, all of the environment variables, all of the bind mounts, and compiles them all together into a JSON file that kubelet can understand so that it can bring up all the containers necessary in concert. Let's look at this even deeper. This is an example SBOM. You can see that it's designed to be extremely human readable, and it contains more than just pods. So it's a superset of the Kubernetes pod spec. You can see at the very top, we start with the base OS. And this is really important to me in JS because when we talk about deploying stateful workloads, we want to talk more than just the containers. The Linux kernel is equally important when you're talking about high-performance data stores. And likewise, the version of the kubelet and the version of all the other things that are running on the host OS are important, and they deserve upgrades too. So they get included in this SBOM. It's not just a pod spec. Next are the containers, which are the actual meat and potatoes of what's going to actually run on this thing. You can see just examples for Cassandra, the preem thing, and the open telemetry agent. And then lastly, we wanted to make sure to point out that we treat configs as a special first-class citizen in our deployment tools. I think this is a really cool way to do it, and I think this is underrated. I think every deployment tool out there should have a first-class position for configs, because often when you're iterating on stateful workloads and you want to iterate fast, it's very likely that the thing you're changing is actually a config setting, not the actual version of Cassandra itself. And because you might have different deployments for different copies of Cassandra or whatever the stateful workload is across your environment, having configs in a special place allows you to not have, say, a different container, a whole different container for Cassandra for dev versus prod versus staging. You can use the same one and use a different configuration. So configs as a separate thing, super cool. So, but that all gets compiled into the SBOM. Or that's the SBOM, it gets compiled into the version set. The version set is, as I said, JSON with all pin SHAs and all the things. You can see that in this case, instead of a tag, they're actual Docker digests, which are immutable and lock that thing in. And these are just examples. And this is an example of a Kubernetes pod spec. Again, that last step where it gets compiled as something Kubernetes can run, which would contain not only all the containers we talked about, but also the configs that get bind mounted in, the environment variables that might be set, and don't forget the data volumes that we mount in from the host. No persistent volumes at play. And while we're not going to be demoing a control plane for you today, it needs to be stated that you still need some control plane. Even if you're not using this particular approach for deploying stateful workloads, some sort of control plane must be at play to be able to gracefully take a MySQL node down, do maintenance, and put it back up into replication. Often, that control plane might be a human doing that work, or if, as you get more sophisticated, a piece of software might be doing the actual controlling, but there must be something that does this work. And in the end, it's going to be something that's going to actually end up with a new pod spec for the kubelet to run on the host. In this particular demo, you'll see JS is acting as the control plane a little bit, but the important part is the runtime to us.
Let's do a demo.
Let's do the demo.
So first, a bit of context. What are we going to demo today? I kind of hinted when I talked about why iterating fast is critical, and this is mostly because of security risk. And so what we're going to demonstrate today is how to apply the two fixes for Log4Shell. And this demo is going to be split in two parts. There's going to be the first part where we're going to demo the update of the sidecar preamp, which is a Java sidecar, using the container replacement with a new SHA. And the second part is going to be, but now that we fix one sidecar, we still need to fix the base OS as well. What if another agent is not containerized and lives on the base OS and is using Java and Log4j? We are going to apply a preventative fix to prevent the vulnerable code path to get executed. While I'm going to do demonstration, think about how we would be able to apply that if we didn't have a high availability system. In this case, since we can actually leverage these two options. We've pre-recorded the demo in case the demo god were not with us today. So first, we're going to make an update on the Docker file for the preamp agent. So we're going to do a simple run command that's going to do a find and then a replacement of the vulnerable, kind of stripping the bad code from the log4j core jar file. That little line will then get pushed to our CI/CD. The CI part is going to be then building a new container. So we'll see that right now. You can see that the fix, the find command was executed. Here is going to get highlighted. And then a couple of seconds after, the image was published to the Docker registry. So again, as Kyle mentioned, I'm going to act as a control plane here. I'm going to grab the SHA, bypass this SBOM, and go straight into the version set. But before that, let's jump on the instance and run. This is just a couple of tail commands to see what's happening right now in the instance. We have the current SHA of the preamp, and the second portion is the Docker PS, and the last portion is the actual logs of the agent. And here I jump into the version set and update the SHA straight here. I'm going to save that. This is our mock control plane right now, just for demonstration purposes. But this instance is actually listening for changes in the version set, and as soon as it receives the change in the version set, it's going to compile it into a pod.json. You'll see that in the logs in the bottom. And then you'll also notice the SHA right now. This is the old SHA. The SHA will get replaced automatically. And then the Docker PS will show that there you go, we got the new SHA. And Docker PS, you've seen it been restarted, and all the new containers are now running for a couple of seconds. And so we just applied the fix on preamp right now. You've seen it was very quick. There's a little bit of speed up because it's a demo, but bottom line, we're talking less than a couple of minutes to get the whole cycle. But again, what we mentioned, that doesn't solve at the OS level, and we're still vulnerable. So we need to apply a second fix at the OS level. The second fix is actually the one that leverages an environment variable that you can set that disable the vulnerable code path. So we're going to demo it here. First, we're going to show the AMI ID on that instance, as well as the fact that the environment variable for deactivating that log4j vulnerability is not available right now. I'm going to grab that. It's not existent right now. Now I'm going to create a new version of that deb file, and we use deb file to bake our AMI. So the first thing is going to be using our custom environment variable injection mechanism we have to set the environment variable globally so that every process on the instance will have that feature flag enabled. So log4j format message, no lookups, set to true. Again, same thing, we're going to commit that, send it to our CI pipeline. In this case, because we're baking in AMI, the process is going to be a little bit longer. But the first step is going to be to actually create that new deb package that will contain all of those, startup script and all of these files. Then once the Debian is published, it's going to trigger our pipelines that bakes a new AMI. So I'm going to demonstrate that right here. The Debian creation doesn't take too long, so I didn't speed that part up. But after, for the bake, it takes a little longer, so you'll see that we're going to fast forward a bit here. So this is the builder getting activated right now.
It's a little confusing because it looks like a Docker image build there, but that's just our CI/CD system.
Yeah, good call out. And here we have the Debian that was generated. We jumped into our Spinnaker system that used for CI/CD. Again, as I mentioned, I speed that part up a bit because it takes about 7 minutes to bake a new AMI and publish it to Amazon. But at the end of that process, I'll be able to grab that AMI ID here, which ends with 158. I'm going to grab that. And now the next step is going to the AWS console. You could use the API for demonstration purpose. I'm just using the console. And on the instance view, I see this is the old AMI right now. I go to storage, and I use the replace root volume button to specify the new image that I just built, I just baked, 158. When I submit that, there's going to be a task that's going to be added. It takes about 2 minutes, pretty quick actually. Our current system for flashing, this is what we're moving to, but our current system that we built 5 years ago takes about 3 times more because we have to do multiple reboots to download the data and all this. But now that this is all in the control plane, this is way faster and more effective. And we can deprecate a lot of custom things we had to build. It's successful here, so I'm going to jump back to the instance that was restarted at the end of that process. And I'm going to, again, show the AMI ID. Should be the 158, exactly 158. And now I'm going to check if the environment variable we wanted to eject is available. There you go, it's available. And now I can go back to sleep because vulnerable is gone. I can resolve my pager and be happy.
Yeah, I mean, I was there with you. I remember where this happened. It was a big deal, and every team got paged. I'm glad that the stateful workloads had no problem deploying because they're deploying all the time, just like the stateless workloads. But for Netflix, it was certainly an all-hands-on-deck situation. It was just, because Netflix deploys kind of all the time, it was just a special circumstance where everyone was deploying at the same time, which was, iffy. But in the end, the act of deploying and practicing that deploy and getting good at it, the stateful workload team, because they've done it so many times, a new deploy isn't that fraught. And they do it all the time. So this particular deploy with a special environment variable, no big deal. We just need to do it and do it fast. I think that's one of the first lessons learned about this kind of thing. Is like it's that practice makes perfect. If it hurts, do it more. And just that kind of good deployment tools allow you to react quickly. I think the other lesson learned here is that we're taking advantage of 2 approaches at the same time for the best of both worlds. That slow AMI bake is replaced with a fast container replacement. But we still have both because we need to be able to replace the kernel. So we're trying to achieve the best of both worlds. We're iterating faster by giving us a fast path for quick deploys when we can with Cassandra and contigs and that kind of thing. But we still have the slower path, which is still relatively fast in the grand scheme of things. Honestly, I've worked at places where the public compile times for the catalog was slower than the amount of time it took you to replace the root volume, get new files. So yeah, there's some trade-offs. But all in all, thank you for the demo. Like they say in Hollywood, it's a wrap. That was the demonstration of how Netflix uses both the flashing of AMI to get underlying OS changes and the replacing containers with standalone kubelet to get new code for the application itself. In both, like in concert, to achieve the best of both worlds, to iterate faster on stateful workloads. And if you notice, if you've been following along with the immutable versus mutable dichotomy, both are in the immutable approach. Technically, you're mutating the OS when you're upgrading a container, maybe. But in the end, you're reflashing the OS like you demonstrated. That's immutable. Every time that you launch a new Cassandra instance, it's going to come up with exactly the same code on boot. The ASG has the same exact AMI every single time. The containers are also, I consider them, an immutable unit of deployment. They're locked to that Docker digest. Therefore, those containers should boot up exactly as all the previous containers did. There's no dependency on Puppet or something to mutate those on boot in order to get them ready for production. So we're still in the immutable world, but we got some speed by choosing containers when we could. But again, this this demonstration and this talk generally isn't really about what Netflix in particular does. It's really about what you should do. It's really about empowering you with the context, the tools, and the options, and the way to think about the cost versus risk versus iteration speed trade-offs in your particular environment, because there's more than one way to do it. Netflix has certainly optimized for a particular risk and iteration speed trade-off that's appropriate for us, which may not be appropriate to you. Let's talk a little bit more about that trade-off in a kind of graphical way. I just love these charts. Take a look at this chart. This is risk on the y-axis and iteration speed on the x-axis. So we're going to investigate all those options we talked about in this kind of lens, in this kind of landscape. I would put Amazon Managed Services all the way on the lower right-hand corner with the maximum iteration speed and lowest risk. And this is why we were both in favor of this option 0, using managed services where we can, because Amazon is taking care of it for you. You don't have to patch it for Log4j. And the iteration speed is also really fast. You really can launch a distributed SQL cluster in seconds. And that's really what they're good at. So if at all possible, I think this is kind of the best option. But as we demonstrated, if you're going to deploy something custom, the approach that JS demoed just now is the standalone containers and kubelet combo. And I would put that somewhere in the middle of the risk and iteration speed kind of chart. And I think this is because iteration speed is relatively fast, depending on what you're changing. The risk is a little high. I mean, there's a lot of moving parts in what you demonstrated. It's not the most simple thing. But again, we've chosen this method because of these trade-offs. We want this. We're approaching the risk-reward, risk iteration speed boundary that we think is appropriate for our applications. Contrast this to the flashed immutable AMI approach. It's slower because you have to bake an AMI, but it's not so slow because you can flash it in a few minutes and then get that reboot. So it's kind of fast, but its risk is lower because there are fewer moving parts. It's still an AMI, and that AMI will boot the same way as it always has, and it's pretty static. So pretty easy to reason out, and you demonstrate it with just the console. You just right-click. So the risk is relatively low on this particular approach, I think. A little even further to the left on iteration speed is the immutable AMI red-black approach that you had hinted at before. This is where you launch a whole new set of nodes, and then you replicate all of the state over. And so during that replication state, I think it has a slightly higher risk because something could go wrong during that replication state. But it is kind of nice because you get all new nodes, which has pros and cons. But this is that approach where the red-black. This is contrast to the flashed immutable instance, the flashed immutable AMIs approach, where when you replace the root volume, the EC2 instance ID is identical. It's the same. The host name is the same. The IP address, the same. So in some weird way, the flashed immutable AMIs, while it's not a red-black, feels a little less risky in some way. There's no state transfer. The Amazon EKS, or just Kubernetes generally approach, I would stick it in the upper right-hand corner. The reason I do that is because of the risk. The risk of this not working and relying on a lot of expertise to get a stateful workload working on EKS or Kubernetes generally, it's high. And it's so high that at Netflix we've decided against it. However, it's hard to argue against its iteration speed capabilities. Kubernetes is fast to deploy new workloads. It's fast to upgrade things. There's a reason it's so popular in the industry. It's a good tool. But again, whether it's the right tool is really about your risk profile and your in-house expertise and all those associated things. Over here is configuration management. We mentioned this with Puppet and Salt and all those tools. I put this up here in the higher risk category because there are even more moving parts to get wrong. And that risk of an AMI starting up and not bootstrapping correctly with those tools is high. So many things have to be done correctly for a configuration management to work well. So a little bit higher risk. The iteration speed, I don't know. It really just depends on your particular environment. I've worked at places where the iteration speed on Puppet was very long. But I've also worked in environments where the Ansible approach was very fast. We can get things done very quickly. You could also break things really quickly. So it's really, who knows? So don't pay too much attention about the x-axis there, but configuration management, yeah, it's a little high risk, I think. And this graph wouldn't be complete if we didn't throw in the classic bare metal sysadmin managed servers. This is just kind of how we used to do it, or how you get started on any kind of classic implementation where you get a node and you install some software and it's running. It's bespoke, it's a snowflake, we all know this, but we still do it when we get started. Everybody does it in the beginning. It's just where do you evolve from there? If you haven't evolved past this point, I strongly encourage you to do so. And I hope we've empowered you with some more options. But this approach is super high risk because if the one person who knows how to set up MySQL instances is not available, you will not be able to get a replacement MySQL instance. The iteration speed is also kind of low because you won't be able to, you're kind of pinned to be able to have changes funneled through a particular human, really. And so, yeah, classic sysadmin. We've come a long way, though, since this approach is becoming since this approach was considered best practice. If it helps, this is a chart-based form of all of that data because it's kind of a lot of data in 2 axes. And again, just reiterating the point on the approach that's correct for your environment is really a function of your history, the expertise in-house, and your appetite for risk and iteration speed. And you can see the standalone kubelet, the iteration speed is high. And like I said, we're here up on stage because we've made that choice that we want faster iteration speed, because we want to be able to deploy new databases and new techniques and new technologies for Netflix games. But at the same time, we want as little risk as we can get away with. So that's why we've kind of emphasized and optimized for the immutable approach, using containers and AMIs where possible, immutable artifacts that you can rely upon, that are locked, that aren't going to change out from underneath you. But you can see all of the different approaches kind of holistically or as a whole when viewed like this. And in case you might be watching a recording, or if you need links to the actual individual pieces of technology that we link to, or the 300% problem, or any of the IPython notebooks that we use to generate the data, they're all available here. And with that, thank you very much.
Thank you.